So yes, this is a very important discussion, and so hopefully I pushed all the buttons correctly and everything to make sure that it'll be captured for people to watch later, because this is going to hopefully give you a good foundation for tackling the last Pintos project, which is to update the file system, upgrade the file system to be much more sophisticated. So let's go ahead and advance the slides. I want to mention, I have a slide about this at the beginning and at the end of this presentation. If you have seniors on your team, we have about 2 days to get your work graded and get the grades in for your course to the registrar. And so we just really want to make sure to ask, if you are hoping or intending to use late tokens on Project 5, regardless of whether you have seniors or not, please let us know, because that will affect the quality of life of Hale and myself. And so, normally we can grade people who turn in on time first, and then we can, if you need 1 token or 2 tokens, it's not such a big deal. But let us know so that we can manage the pain of that experience properly. So I certainly want to make that request up front. Okay, the initial Pintos file system is limited, as you probably have read by now. Files are contiguous regions, so you have a start sector and a length, which is used to calculate the total number of sectors in the file. They cannot grow, so they're limited in the ability to be extended. There's only a single directory, which can only hold 16 entries, so you can't have path nesting. And so that is one of those issues. You may actually see some issues in your initial stack setup if you happen to manage information improperly in stack setup, because paths will be able to be much longer once you have nested directories in Pintos as well. So there's a number of real issues that occur. Oh yeah, and then we have a global file system lock, which we're going to touch on multiple times as we go through this discussion. So you need extendable files that don't need to be contiguous. And the recommended approach is to actually support files who can have any sort of structuring of blocks possible. So we do this through this Inode data structure, which I briefly touched on, but you can go back and review the slides. I'll mention some details of that as well. Directories that can grow to hold more file entries as needed, directory hierarchies, and then fast concurrent access from many kernel threads. And the primary means by which we achieve the fast concurrent access is through the introduction of a file cache, a file system cache that supports read-write locking, so that readers can proceed concurrently, and then writers will block everyone else when necessary. So that's the idea there. There is a suggested order of implementation in the project write-up. The buffer cache is recommended first because it can be done. It should be transparent once it starts working. And it forces you to think about some of the hard concurrency problems initially, which is always the way you should design these systems. Never try to design a system and then later make it concurrent. It's a terrible approach. And because concurrency affects the design of APIs, it affects the structure of your program in ways that you may not discern until well after it's too late. And so you always want to try to incorporate concurrency up front when you're designing systems. Extendable files is recommended as second. The recommended approach is to use something like ext2. It is required that it be a multi-level index file layout. If you decide to do a 2-level index for all accesses, you're free to do that. But the reason ext2 is recommended is because it is a historical approach that has worked very well. There's plenty of documentation about it, and the way you can implement it is not too complicated. So we'll talk about that. Oh, and there's a giant note here. Files do not need to support shrinking or truncation, which means files can only grow. And since files can only grow, you can take advantage of that in your implementation. So we'll touch on that as well. Subdirectories, and then remaining miscellaneous items like the current directory that a process is running in, so that you can change the working directory, have relative paths, and so forth. Parsing and navigating directory paths, read ahead and write behind. So that stuff generally tends to be pretty easy, with the exception of the current directory of the process, because you have to think about how to keep the reference that the process uses when it's doing directory relative operations. Okay, items 2 and 3. The assignment write-up suggests that items 2 and 3 can be done in parallel, but you need to be very cautious if you do pursue these things in parallel, because you need to make sure that you don't get too isolated from teammates' efforts on these projects or on these sub projects. So it's really crucial that when you're building anything that you are merging frequently to keep up to date with the state of the art in the code base. And we've seen a lot of projects, a lot of teams over the years who basically do steps 2 and 3 in isolation and then try to merge them together, and it's catastrophic because both of these things affect each other. And so making sure to do them with consistent merging is the way to avoid horrific merge conflicts and merge pains at the end of the completion of these steps. Work in an integrated manner all the way along. So that is a huge important thing for you to be aware of up front. Okay, file systems should support concurrent access. So that means that we have files being read and written by multiple concurrent processes. This will be done very aggressively by many of the tests. So you have a couple of things that have to work well. File extension has to be atomic, because if it's not, you'll have mangled file contents. And a lot of times it manifests as multiple reads that are in the same region instead of properly extending the file each time. And so there are some tests that hammer on this pretty heavily, and I have a suggested approach later in the discussion for how to do this. And also, readers should not block other readers ever. And if you can achieve that, then you will have satisfied the requirements of the concurrency aspect of the project. Writes to different parts of a file shouldn't block each other. So if I have a write to the first part of a file and another process is writing to a subsequent part of the file, but they do not overlap, then they shouldn't block each other. Those writes should be able to proceed concurrently. And you'll notice that I say here, this can be true on a per sector basis. What I mean is if the write involves multiple sectors and then there's another write that includes multiple sectors, the concurrency may be on a per sector basis, because ultimately you update the file on a per sector basis. So the concurrency, you can think of it as proceeding on a per sector basis. Reads shouldn't see written data until the write is completed. And again, this is on a sector by sector basis. So if a write is covering 100 sectors, then it doesn't mean that a read in that region shouldn't see any of the sectors that were written. It just should see complete sectors written, not partial writes or weird bogus updates as they occur. Basically, on a per sector basis, a read shouldn't see, it should either not see the write or it should see the entire write, is the way to think of it. And you don't need to do anything at a larger level. Real operating systems have to think more carefully about this, but we can keep it pretty simple. Your sector is your unit of work when it comes to your file system. All right, directory operations on different directories should be concurrent. This is a pretty challenging one for reasons we'll talk about. And you may not have a global file system lock that serializes file system access like you start with in Project 3. You also have to be careful not to have any other kind of global lock that inadvertently serializes access. This is, again, one of those things that we check for by inspection, And so it may be that you accidentally do this, but if we don't catch it, then you win. But we're going to be looking for this kind of thing. And I'll spell out some of the kinds of patterns that generate these unintentional serializations of the interactions with the file system. But the number one thing is you better get rid of your global file system lock, or else you'll definitely incur this penalty. Okay, the cache is straightforward to implement for the most part. You are given a specific size of the cache, 64 cache blocks, and I say on this slide, file data, metadata count against this limit. What do I mean by the metadata? Well, I mean the inode, the indexing structure that that says what blocks to access in the file for a given logical offset from the start of the file. I say you can exclude the file system free space map. Well, the free space map is going to occupy, I think I calculated a total of 5 sectors. So you can exclude it or not exclude it. Nobody's going to care. You may also cache that information in memory. It's up to you. It's your call. I don't know why the Pintos assignment even says this stuff, because to be honest, why be more clever than you absolutely have to be? Cleverness is usually what generates bugs, and bugs make you stay up late and turn in work late. So it's like, keep it simple. That's always we have this thing in software engineering called the KISS principle. Keep it simple, stupid. And it comes from the military, like the 1960s, and it is a rule of life when you're a software developer. So don't worry about all that fussy stuff like data, metadata, free list, any of that kind of stuff. I would just build it and use the file system cache for all interactions. Okay, like I say here, you need a dirty bit because you may have writes against a block in the file system cache, and you need to make sure that when you evict the contents of a cache entry from the file system cache, that it gets written back to the file that it came from. At that level, it'll be a sector. So that's a lot easier than virtual memory. You don't have to be clever and say, oh, swap, oh, file, oh, whatever. You just know it's a sector. You just plop it back to the sector on the device. That's easy enough. So here's an idea for an approach. Build a cache and retain the global file system lock. Get your cache working and have everything interact with the cache. So if you do that and then get all your tests passing, you can be pretty sure that your cache will work properly. At least functionally, it will be correct. Once you do that, you can get rid of the global file system lock, and you can switch to cache entry locks. Because if you're using cache entry locks to properly ensure correctness, then you've gotten rid of your file system lock, your global file system lock, and you can, again, you will have made one small change, and then you can run the tests again and see what tests are failing and address those failures. So the important key here is the way to make your life simpler with debugging is like any scientific experiment. Change one thing and then see what catastrophe you created. And if everything continues to work, you're good. And if everything starts to break or things start to break, you know what code you changed to cause the failures. So you know where to debug. And so that's why it's so crucial that you think carefully about, like, don't make 50 changes at once. Make small numbers of changes. Rerun the tests. See where you stand. So that's a strong recommendation for everyone. Okay, finally, any more advanced concurrency issues to resolve? Because you will start to run into other concurrency issues, file extension, directory access, and probably a few other things as well. Now, there's 2 ways you can do the file system cache. There's the easy way, hint, hint, you should totally consider doing this, which is just having a statically allocated array. So in one of your .c files, you'll have an array of 64 entries where each entry can hold a block of data. So that ends up in the kernel memory allocation. So that's going to be kernel pages. Why not do it? Or you could use a hash table that maps to entries, or you could have a combination, right? You could have a hash table that stores the index of the sector in the statically allocated array. You could get very fancy if you want, but you probably shouldn't. The thing that I want to mention here is that the grading guidelines for this project, and these are the grading guidelines from Stanford, which I actually don't follow. I'm significantly more lenient on the code inspection component of this course than the original Stanford material. And the Stanford grading guidelines say it's perfectly fine to linearly search through 64 entries, because the assumption is it's capped at 64, so it's constant time, at least as far as the file system. It's not linear in the size of the device or anything like that. Obviously, it's linear in the context of the cache size, but we fix the cache size at 64 entries. So if you want to just have an array and linearly search through it, you're not going to get any complaints from us, and it'll be simple. So it's something you may want to consider when you're doing this stuff. Okay, you do need eviction. Clock is a perfectly reasonable choice for the eviction policy again, and you've already implemented it once, so hopefully all of you realize it's really not that hard to implement clock. And if you want to be fancier, you can be, but I wouldn't do it until you have everything else working pretty dang well. Okay, I just heard my Facebook Messenger ding. I don't know who that might be. So maybe my friends in Australia, who I believe are just waking up. So yeah, there are a lot of other policies. I'm not even going to talk about it, because why? Do this if you have everything else done way in time and you want to be a little bit fancier. Now, there are concurrency scenarios you need to think about with your file system cache. And one of the things that's more challenging about the file system cache is that you can have multiple processes concurrently accessing cache entries. And so that means you need to think about read-write locking. That's one big concurrency issue that is a part of the requirement for the project. The other big concurrency issue you need to think about is one process accessing a sector and another process who's trying to load something, a different sector, and the file system cache decides to evict the sector that first process is trying to access. So this is the same scenario you had with virtual memory. Process A wants to read sector 234. The cache has a global hash table because you decided that would be faster than a linear scan to look up which cache entry contains the sector. Meanwhile, process B has determined that sector 216 is not in the cache and wants to load it. And so it needs to evict some other entry in the file system cache, and sector 234 was chosen. So now this is the challenge. Process A is trying to access the entry. Process B wants to try to evict the entry. So if you have a hash table, so you have this hash table mapping sector numbers to entries in the cache, right? It may just have the index of the cache entry or something like that. So it's an easy way to do a single step to see if an entry is in the cache. You don't have to do a linear scan. You may want to, so you have to think about this question. If you use a hash table, how do you guard concurrent access and modification to the hash table? Because the hash table will be completely annihilated if you have unguarded concurrent mutations of the hash table. Here's another possible approach. Can a process get a file system cache entry and then suddenly discover that the entry contains a different sector than it thought it contained? Now, you may read that point on the slide and say, that sounds like it would be a bug, because you look up in the hash table, I need sector 234, it's in cache entry 21, and then you get to cache entry 21, and it's got a different sector other than 234 in it. But there are solutions that have that characteristic. And so you may say, this entry didn't contain the sector I thought. I'm going to go back and try again. So you have these kinds of interesting scenarios. So you have to think about how you interact with these mechanisms and how you use locks to guard them. Okay, so this is the issue. If you have some kind of hash map for doing this kind of mapping, and you have a global lock to guard it, then you may have designs that introduce issues. Like here's a simple example. You acquire a global lock guarding the hash table for the cache. This is not the global file system lock. This is just a lock guarding some shared data structure. You find the block in the cache, then you acquire the lock on the block because you say, you know what, I need to make sure that mapping doesn't change. So you go ahead and acquire the lock. You release the global lock, you perform I/O on the block, and then you release the block's lock. So we call this crabbing because it's like the way that crabs walk sideways. You have a place where you lock something. This is the global lock. You use that global lock to take your next step, and then you lock the second thing, and you don't release the global lock until you've acquired the lock on the second thing. That's called crabbing in a lot of different contexts. So it's a very reasonable approach. It's a natural, intuitive approach, and a lot of systems use this kind of approach in many different contexts. But in this context, it breaks things. So basically, here's the scenario. Kernel thread 1 performs a read on block B. Kernel thread 2 decides it wants to evict block B or anything else that it needs to do on block B. And then kernel thread 3 performs I/O on any other block in the system. And so this is the way that this scenario can unfold. Kernel thread 1 acquires the global lock because it's looking at the mapping, the mapping hash table. It looks up block B's entry in the cache. It says, it's over here. Then it tries to acquire block B's lock, and then it releases the global lock and starts reading data into block B. Kernel thread 2 comes along while this is occurring. Remember, the read is going to be very slow. So kernel thread 2 acquires the global lock. It's going to find block B in the cache, and then it will block on block B's lock. And so it's waiting for kernel thread 1 to finish its long-running operation. But it still holds the global lock. And so kernel thread 3 comes along, and it wants to do anything else with the file system. But unfortunately, sorry, my wife just got home and the dog is excited. So kernel thread 3 comes along and tries to acquire the global lock guarding the little hash table that you thought was a safe idea. And now you have forced the entire file system cache to serialize certain sequences of operations by accident. And so this is a bad design. This doesn't satisfy the concurrency goals of the implementation. So the issue is that we wait to release the global lock after we acquire the lock on block B, because that's what causes the second kernel thread to block on B's lock while it's also holding the global lock, and then that blocks other threads. Okay, so we have to think, is there a way that we can reorder the locking and unlocking to prevent this unfortunate performance issue? Okay, and like I say here, sometimes other threads are doing really slow things with the entry, so the entry lock is becoming a blocker for other things holding the global lock. Okay, so what if we change this? You'll notice that we made one tweak right here in the first column. Kernel thread 1 gets the global lock, looks up which block holds, which cache entry holds that block's information, releases the global lock, and then acquires B's lock. Okay? Now, some of you may remember that I would squawk at you when I looked at your virtual memory implementations because you'd have, the frame table lock, and then you'd acquire the lock on the frame, but you'd lock the frame after you unlock the frame table. And I said, are you sure you want to do it in that order? But in this case, you may in fact want to do it in this order, but it does allow potential interleavings that yield unexpected results. And so I want to show you what can happen, because you can have kernel thread 1 acquire the global lock, figure out that it wants to operate on a particular cache entry, but in the meantime, some other kernel thread has swooped in and it's decided that it wants to do something on the same cache entry. Notice here we evict the block from the cache entry before kernel thread 1 gets to use it. And so kernel thread 1 gets to the cache entry and it doesn't hold the block that we're looking for any longer. So what do we do? What might we do in this situation? And there's a very simple solution that we can do, which is just check that the block, let me try to say this really clearly. Check that the cache entry still holds the block that we're looking for after we've acquired the lock. So down here, instead of saying acquire B's lock, we introduce a new step immediately after acquiring the lock that says, are you still block B? If you're not, go back and try again. So you just sort of iterate on your mechanism. Okay, so after the thread acquires B's lock, simply verify that the cache entry still holds the block we hope it is. That's all you need to do to get this to work properly. So if the cache entry no longer holds block B when the thread gets the cache entry lock, just go back to the hash table and try again. And if you lock block B's entry again, you check it again and it's not the right one, you try again. And fortunately, this is not a situation where you should see very severe starvation issues. This is generally called optimistic locking because you are hopeful and you're optimistic that most of the time, nobody will have beaten you to the punch. So that's what we're doing here, is we're doing an optimistic locking mechanism. But you just have to be careful that when you get to the cache entry, you got to double check that it's the thing you hoped it was. Okay, so that's the key detail there. Hopefully that helps with everyone. Now, the other part of this, which is that readers shouldn't block readers, is typically implemented with a read-write lock. And it's also known as a shared exclusive lock for obvious reasons. I mean, it just, writing should be done exclusively and reading can be a shared operation, but there may be other scenarios where you have one kind of operation that can overlap and other kinds of operations that must be performed exclusively, which is why you call it a shared exclusive lock. Pintos does not include one, and it's by design because they want you to learn how to implement a read-write lock. What most students do is they get on Wikipedia and look at how Wikipedia describes a read-write lock, and they build that. And that's all you really need to do. I just want to mention a few details of this, and I'll probably skip over a lot of this just for the sake of time. You want to think about fairness for both readers and writers. You can have a situation where you have some number of readers holding the lock, and a writer comes in desiring the lock, and new readers keep showing up and keep hopscotching over the writer because there's readers holding the lock. So you want to think about that. That can produce starvation for the writer. You can also have situations where if a writer is holding the lock and readers come in and a new writer comes in, that you can accidentally design the lock such that if a writer releases the lock, that it hands the lock to another writer. So that starves readers. So you need to think about these kinds of scenarios that can occur. Currently held by readers, lock released by a writer. Always try to make sure that you're moving back and forth between readers and writers in some efficient manner so that you don't end up starving one category of lock requestee, if you will. Okay. So one of the details of this is you don't need to necessarily respect the global ordering of lock requests. And it turns out that it's usually easier to design an unfair lock than it is to design a perfectly fair lock. And so most of the time in systems implementation, we don't try to design perfectly fair locks. So just make sure that you avoid starvation. That's the number one requirement and goal that you should really aim for. There are a lot of different ways to build a read-write lock. The number one thing is make sure you encapsulate the state, like in a struct, so you can plop that into your cache entries. and make sure you encapsulate the the lock acquire, the lock release operations. That will save you so much trouble. Okay, yeah, Pintos, this slide basically just says, hey, you've got all of these primitives in Pintos, use them. Use your standard locks, your mutex locks, and use your condition variables for implementing the read-write lock, and your life will be pretty golden, okay? I think I've seen implementations that use semaphores as well. I'm trying to remember. Don't quote me on that. Like I said, do a little bit of research, look on Wikipedia. Pintos has all the tools you need to build a read-write lock very effectively. So I would probably do it with mutexes and condition variables, but I've been doing concurrent programming for many, many years. And I know that's a pretty low-level way of doing it, that I can get exactly what I want. So just read what Wikipedia says about the topic and pick the approach that is most intuitive to your team. Okay. Yeah, this is one important detail about condition variables. Condition variables can go off spuriously. They also can go off and another requester comes and swoops in before you know it. And so the important detail here is you always want to check conditions in a loop that waits on the condition variable, not just assume that if you wake up on a condition variable that the condition is now true. So verify when you've waken up that the condition is actually true, and if it's still not true, just go back to waiting on the condition variable. Just do it in a loop, okay? There's a lot of interesting buggy examples of that rule at work. So just keep that in mind if you use condition variables. Okay, read ahead and write behind. These are super straightforward things to implement, but still you want to leave them until after everything else is sort of starting to fall into place. Read ahead is just that if a process requests a sector, that you automatically prefetch the next sector. Now, when we say the sector, we mean the sector in the file contents, not the next sector on the device. So if because remember that files aren't necessarily going to be contiguous anymore, but a lot of times they are scanned sequentially. So when a particular file read is done, you can look up the next sector in the file's contents and queue up a read of that sector as well to get it into the cache, okay? So then write behind is very similar. Basically, you periodically traverse the entire cache and write dirty cache entries back to disk so that they end up being written out on a periodic basis. Now, this is the one place where the timer work from project 2 could be useful, because you don't want, like what you basically do, let me see, both of these things happen in the background. So you just create a kernel thread that gets started at initialization time, and that kernel thread's job is to do read ahead or have another kernel thread that does write behind. And so what you want to do, let me see if I actually talk, I do talk about this on subsequent slides, but I may skip over some of that detail. When you're building the read ahead, you can just have some kernel thread that issues read operations for you. And if the read operation is using your file cache, it automatically all just works. So the read ahead thread is pretty easy to build. Write behind is only slightly more complicated, because you just have to periodically traverse the cache, identify dirty pages, and try to write them back to disk. So you basically just issue a write for those kind of pages. That's it, right? The only issue is write behind should do this on a periodic interval. So that involves the timer tick. And so you want to try to build this in a passive way. And so this was why in project 2, it said you might find the timer handler or the sleep mechanism useful for project 5. You can also just hard code in the timer tick interrupt handler to say, hey, has enough time passed? Let's go ahead and do write behind or kick off write behind. So you can build it in various ways. Just don't actually do the writing from the timer tick handler, because then you're going to delay the interrupt handler and everything will go haywire. So just think about how to build that But both of these are pretty straightforward mechanisms to build. Okay, read ahead. So a kernel thread is spun up. What you can do is have a queue. You could have a circular buffer. You could have a linked list. You could do it in a couple different ways, but just have a queue that other threads can put sector numbers onto the back of the queue. And this kernel thread just checks the queue. And if there's something in it, it pulls the sector number off and does a read on that sector number. And that's all it does, because that'll automatically load the cache. Okay. So you need to think about the concurrency implementation. And this is a great place to use a condition variable, because the thread that is asking for the read ahead can just plop the sector number into the queue and then signal on a condition variable. The kernel thread that's waiting can simply wait on the condition variable, wait for signaling on the condition variable, and when it gets signaled, it can go ahead and figure out what sector it needs to read. So you have a pretty straightforward mechanism there. WriteBehind, another kernel thread. I already talked about this. It's in a loop, sleeping for a specific period of time, wake up and write back any dirty sectors in the file system cache. So that's the thing. Make it passive waiting. And if you trust your timer tick implementation, you can just suck that into Project 5 and leverage it for doing the WriteBehind implementation. Because I think it's like every second or something. I can't remember precisely what the assignment suggests. Okay. Extendable files. So you need to update your file system to support file extension and non-contiguous extents. So both of these things are going to require the ability to allocate a single sector from anywhere on the device that is currently available. So you'll need the free space map to work, and you'll need the inode structure to be more sophisticated. Right now, it's very simple. It just says what sector the file starts in and the length of the file, which you divide by 512, rounding up, and that tells you how many sectors total comprise the file. So you'll need to change the inode implementation. So the thing that I want to tell you is don't be afraid to change inode disk and inode, these two data structures, based on your needs for this project. A lot of students initially get kind of scared because they're like, the file system works and I know I'm going to break it if I change things. And the answer is yes. Feel free to just dive in and start changing things as you see fit. The free map, as an example, can continue being a bitmap, but you probably want to change free map allocate to only do single sector allocations, because free map allocate also can allocate chunks of sectors, and you will need to support individual sector allocations pretty much universally going forward. Okay. So here's one of the things that you need to be aware of. The file system partition has a cap of 8 megabytes, or 8 binary megabytes. So whatever that is, 8192 times 1024. So you can do the math and figure that out. Files can only be a maximum of 8 megabytes. So take advantage of this limitation. If you do the math, you discover that this is 16K 512 byte sectors. So you really only need to think about a maximum of 16K 512 byte sectors in various contexts. One implication is that the free space map only needs to be up to 4 sectors in size. Now there's also an inode, because the free space map is stored in a file. So that means your free space map will only ever really take up to 5 sectors worth of space on your file system. File inodes need to be able to index up to 16K sectors, because that's the maximum number of sectors that a file can occupy. And so this means you need a multi-level indexing structure. If you figure out like how much space the metadata for the file takes, and then the rest of it can be block numbers or sector numbers on the device, you figure out how many of those you can hold, multiply that by 512, that's the maximum file size you can support with a single sector inode. And you will find out very quickly there isn't enough space to support 8 megabyte files. And so you will require a multi-level indexing structure. Now, let me see. Yeah, the free space map is a specific, so this is just some useful information. And this is actually really helpful because you'll notice that its inode is hard-coded by the OS. The inode always resides at sector 0. So Pintos has a simple mechanism. The free space map is a file whose inode is at sector 0. The root directory is an inode at sector 1. And so this is also why the current limitation is 16 files and a single level directory structure. Files can't be extended in Pintos until you add it, so you can't have a big root directory and you can't have nestings of directories as well. So this is something that you'll have to fix. The inode is a special indexing node. That's what inode stands for, index node. And so the inode itself will also occupy multiple non-contiguous sectors because you'll have the starting point, the root of the inode, which has some metadata and also some direct and indirect block references. The indirect, single indirect and double indirect blocks will be in other sectors, but it's still part of the indexing structure for a file. So inode.c has two different inode data structures, and this again often confuses students. Inode disk is the version of the inode that's actually written to disk and read from disk. So this is always going to be 512 bytes on Pintos. Now there's code in the file system that takes the inode disk stuff and unpacks it and has additional memory-only things that are used by the kernel, like locks, like other details. Who is using this inode? So that's what the inode data structure is. And again, you can change the inode data structure as you need to support the more sophisticated mechanism. Okay, so the inode structure initially has an inode disk member, but this is before you add the file system cache. And I want to mention this because once you have the file system cache, that inode disk really should no longer reside in the inode. The inode disk should be kept in the file system cache, but that means it's just going to be a block of 512 bytes. And so you will look up against the cache and get the cache entry, probably locked or pinned or something like that, so that you can work with it temporarily while you do your read or your write. You'll use the ReadWrite Lock for that kind of a thing. And so you can just take that array of bytes and cast it into an inode disk star. Cast it into an inode disk star, and then you can interact with the parts of the inode disk structure appropriately. So that's the recommended solution. That's sort of what your solution will look like. So that's one part of the inode that will go away. You can immediately know that the inode disk inside the inode will start to reside in the file system cache instead. Okay, let's see. Yeah, so the assignment suggests something like ext2. I want to mention that the Wikipedia article on ext2 is actually pretty dang good. It's got some good pictures to help you understand why the approach works the way it does and how it's laid out. So you'll understand what I mean when I say a multi-sector inode, because there's a root to it, but then there's portions of it that become a tree if a file gets too large. Okay, so the inode references, besides metadata, some number of direct nodes, some number of single indirect nodes, which means you have another sector that's part of the inode, and it says here are sectors in the file. And then some number of double indirect nodes, which means the inode has a reference to a sector, which points to other sectors that also contain indexing information. And then the second level index points to sectors in the file contents. You can look at the file system lecture. It was 1 or 2 lectures ago that describes that data structure, but the Wikipedia article is also really good. Now, a single direct node cannot represent 8 megabyte files. The absolute most that you can reference from a single sector is 64 kilobytes because each reference is going to be 4 bytes. You divide 512 by 4, you get 128 entries in your little index, and 128 times 512 gets you 64 kilobytes. That's not big enough. You have to support 8 megabyte files. And so that's why some number of those entries have to point to other blocks that also point to sectors in the file. And if you do that, then you get up to maybe 100 kilobytes. That's still not big enough. So then you need the double indirect blocks to get up to the full 8 megabytes that's required by the assignment. It is up to you to decide how many single indirect and double indirect entries to use. The hint is use as few as possible. And a further hint, since you are listening to me talk, is I think you can get away with 1 single indirect block and 1 double indirect block. In fact, I think you could get away with only 1 double indirect entry for the entire index structure. And you certainly could do that, but I don't know. We might be generous and just let you do that. But it's still, if you do just a single double indirect entry, then it becomes really slow for small files. That's why it's not recommended. And that's why ext2 has the design that it has. Small files are fast, medium-sized files are a little slower, and then large files are very slow. Because remember, when you're navigating this indexing structure, you have to do disk accesses to look up the next levels of indirection. So that's why ext2 has the design that it has. Okay, let's see. So here's some examples. You have how many direct block entries do you have? How many single indirect entries do you have? How many double indirect entries do you have? And then your total number of entries is just those things added together. And then you could either have everything in a single array, sectors, num entries. So this is the contents of the file in your Inode disk. Or you could have multiple arrays, something like this. The reason why I'm describing this is that both of these approaches will have the same disk layout, but the benefit of the Inode disk version, or the second Inode disk version that I have, is that you can look at the code and tell, I'm working against single indirect blocks. I'm working against double indirect blocks, so that it's very clear. This code is going to be hard enough to write as it is. And so you might want to think about how you can improve the clarity of your code as you do this file, So basically you'll have an operation where you have to take a logical offset from the start of the file, turn it into the sector you need to access. And that operation is going to be a little bit complicated to implement. So just think about how you can make the code as clear as possible so it's easy to debug. Okay, let's see. File extension by multiple processes. This needs to be atomic. And the reason why is because if the file length doesn't change when the file extension occurs, and that all happens atomically, then multiple processes extending a file will corrupt the file. And there are definitely tests that hammer on this. So what this means is that the in-memory inode needs a lock for governing file extension. A lot of times people just call it the file extension lock. So we need to make sure that other reads and writes inside the file's contents, not at the end, aren't blocked by this extension lock. Okay? Because remember, that's a rule for the concurrency requirements. If every interaction requires this extension lock and holds the extension lock, suddenly you have a performance issue in your file system and you need to fix that. It violates the rules for the assignment. So you need to check the file size to see if a write is going to extend the file or not. And this is where you have this great simplifying constraint, which is that files can only grow. So if you have a situation where you know you're in the middle of the file, you will continue to be in the middle of the file for any subsequent operations because you can never go backward, you can never move, you can never truncate the file so that a write into the middle of the file suddenly became an extension operation. If you have an extension operation, it may continue to be an extension operation, or someone may have beaten you to the punch. So it's only when you're extending that you need to think about this. If you're already in the middle, you know you will continue to be in the middle of the file. Okay, so two main choices. Always lock the file extension lock before checking the length. As I mentioned, this will create some issues. Like I say, it's easy to get right, but the drawback is you have to acquire that lock for everything. And so if you have several writers trying to extend the file, the writes to the interior will be blocked until they can acquire the lock. So this approach is kind of unacceptable. Now, the other approach is to use this pattern called double check locking. And I think it's great to be exposed to this pattern. So you'll notice what we're doing here. If the write position is at least the length of the file, well, then we may be extending. Notice we haven't acquired any locks. We're doing something slightly dangerous. If it is, I should say, if it appears to be at or past the end of the file, then we acquire the file extension lock. And we repeat the, sorry, I just had something cross my brain. So you check again. If you've acquired the lock and it is an extension, now you know you're extending the file, and you go ahead and extend the file in an atomic manner. So that's the way to do this. It just reminded me of Tweety when he would say, I taught a putty tat. And then he said, I did taw a putty tat. It's the same thing. It's double check locking. You probably didn't know that Warner Brothers cartoons had that mechanism as well. So anyway, you can see here that so if you check to see if you are extending the file, and then you get in here and you find you're not extending the file, then you can go ahead and release the extension lock right away. And you now know that you're extending, or you're writing within the interior of the file. So this is the double check locking mechanism. And it's a strong contender for a good approach in this implementation. Now, the one thing that you have to be concerned about is that you have two comparisons of some value. In fact, you have two variables that you're looking at. One's in a struct and one is a local variable. So the thing that you have to be aware of is the compiler will think, why are you checking it twice? It won't change. So it may optimize away the second check, or the second check may not actually involve a memory access. And so because of that, you have to make sure that you declare these things volatile, or cast them to volatile, so that you force the compiler to do the read both times. So that's really kind of the crucial detail you need to be aware of. If you use double check locking, you have to use volatile to make sure that the compiler doesn't optimize away one of the memory accesses. Super critical. Okay. All right, let's see, a few other things. So you do need to think about order of operations. Unfortunately, I'm running out of time. I just want to ask, I have to run too. I have an appointment at 2:30. I'll just see if there's anything else that's really crucial to talk about in here. You can read that slide. I think it'll probably be straightforward to consider. Directories in Unix are just files with directory information in them. So you can have like file name and the sector of the file's inode and any other information that needs to be tracked through the directory entry. So you'll just notice that when you get into the implementation, there will be some files that are of type file, regular file, and some files that are of type directory. And that basically is all you really have to do when you're trying to figure out how to do a directory. Okay. That's actually how Unix does it as well. When you open a directory, scan a directory, it's a file on the disk with special semantics about how the contents are interpreted. Okay, let's see what else. Yeah, the concurrency on the directories is also challenging, and so you definitely want to pay attention. Like if you have a global collection of directories, that can generate concurrency issues, because then again, you have a global lock guarding that global directory, and that can produce some issues. And so you need to think carefully about how you manage the concurrency of these of this part of the system. because Pintos's requirement is that concurrent operations against different directories should proceed in parallel, or concurrently, I should really say, because there's only a single core in Pintos. But operations on the same directory should be sequential, as one would expect. Okay, the rest of this I'm just going to leave for you to review on your own. I guess the one thing I would say, in fact, that's the last slide, or the second to last slide. This is the last slide. But feel free to ask for any help. I realize that the review, we always go over time with this review. So just ask if you get stuck on anything or have any conceptual issues that you want to resolve with us. Feel free to use Piazza so that everyone benefits from the questions. And as I said before, please ask if you need late tokens, because we're under a time crunch to get the grade. We try to set the due date as late as possible for seniors, but then that affects things if anybody needs to use tokens. So just ask if you are in that situation. All right, that's all I have to say. Good luck, and I'll see you Friday for the last CS124 lecture.